Hello everyone and welcome back. Today we are tackling a really interesting medium level Leetcode problem. Design add and search words data structure. Problem number 211. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we have to design a data structure that supports adding new words and finding if a string matches any previously added string. We will represent it with the WordDictionary class, where calling the constructor initializes the object and the addWord function adds a word to the data structure and the search word function returns true if there is any string in the data structure that matches the word or false otherwise. Word may contain dots, where dot acts as a wildcard and can be matched with any letter. For example, here we create the word dictionary and add the words bad, dad and mad to it, and later we search for the string pad and it should return false because we never added pad. But if we search for bad, we will return true because it's a simple exact match. And later, if we search for the pattern .ad, we should return true. Why? Because this dot can match B in bad, D in dad or M in mad. So we have at least one word that fits the pattern and hence we will return true. Similarly, if we search for the string B dot dot, we will again return true as it matches the word bad, where B is the exact match and dot dot matches characters A and D. And in terms of solution, one of the naive approach can be to store these words into a collection like a list or set. Let's stick with a simple list for now. And when the addWord method is called, we just append the word to our list. So here for example, we will add the words bad, dad and mad to the list. The real work is in the search function. To find a pattern like .ad, we will have to check every single word in our list. First, say we pick the word bad and we check do the lengths match and the answer is yes. Now we will compare them character by character. As the dot is a wildcard, it matches B, then A matches A and D matches D. So we found a match and hence we can stop and return true. But what if the search fails? For example, consider the pattern .ag and we check this pattern with the words in the list. So we check it with bad, no match, then dead, also no match, and finally mad, again no match. So only after checking every word can we finally return false. And this is where the problem lies. And you might think that using a set would help. That's a great thought for handling duplicates or exact searches, like searching for the string bad, because in this case the lookup takes O of L time, where L is number of characters in the string. But for a pattern search with a wildcard, a set doesn't help. We still have to iterate through every single word because just like with the list, the wildcard breaks the set's fast lookup mechanism and that reveals a huge bottleneck. No matter if we use a set or a list, in the worst case, like with our .ag pattern example, the search time complexity will be O of n into L, as we have to look at all the n words and for each word we might look at L characters. And if our dictionary has million words, that's a million checks for every single search. So this approach is simple and it works, but we need to find a better way. With every search, we are re-evaluating prefixes over and over. For example, if we search for apple, our naive method wastes time checking words like banana or car, which don't even start with the letter A. What if we could organize our words to take advantage of shared prefixes? For instance, knowing that apple, apply and ape all start with AP. By structuring our data this way, if we search for a word, we could navigate through a common path and instantly ignore any words that don't share that same prefix. This is the exact problem that a trie data structure is designed to solve. A trie, also known as a prefix tree, is a special tree for storing strings, where each downward path from the root represents a prefix. We have covered the trie in detail in our implement trie video. So if you need a refresher, be sure to check out the I button or this video's description. So how do we build this trie? Well, we start with an empty root node. This is the starting gate for all our words. It doesn't represent any character itself. And now, let's think about the information each node needs to store. It really comes down to two things. First, pointers to the next characters, as it needs a way to link to the next possible characters in a word. And here, since we are dealing with the lowercase English letters, a node can have up to 26 children. In Java, a simple array of 26 trie nodes is perfect for this. In Python, the more idiomatic way is to use a dictionary or a hash map to store the children. And second, a trie node needs to signal that a word ends here. We need to know when we have formed a complete word. For this, we will simply use a boolean flag is end of word. So in the constructor for WordDictionary, all we do is to create a single empty trie node and set it as the root. Now say we want to add the word bat into the trie. So we start with a pointer to the root node and the first character is B, and we check if the root has a child for B, and the answer here is no. So we create a new trie node for B and link it to the root and move our pointer to B, and next character we see is A, and we check if the node B has a child for A, and the answer is again no. So we create a node, link it and move the pointer to it, and the last character is D, and we do the same thing, create node D from node A and move the pointer there, and now we are at the end of the word. So we must signify that this path forms a complete word, and hence we will set is end of word flag for the current node to true. Let's take some more examples. Let's add the word dad to the trie, and again we always start back at the root and check if the first character D exists as a child for the root node, and the answer is no. So we create a new node and link it to the root and move the pointer to D, and similarly we will insert A and D into the trie and mark the last node D's is end of word flag to true. Similarly, we will add the word mat to the trie, marking the final D as the end of word. And finally, let's see one more insert example. This is where the trie truly shines. Let's say we need to insert the word bat into the trie. So again we start at the root node. Now first character is B, and we check if the root has a child B, and the answer is yes this time. We have already created it when we inserted bat. So we just follow the pointer to the node B, and from the node B we check if there is a child for A, and the answer is yes again. So we move our pointer to node A. Next character we see is T, and there is no child for it. So we create a new trie node for T and link it to A and move our pointer to node T. And since T is the final character, we mark it is end of word flag as true. Notice how we have reused the entire BA prefix. And that is the magic of the trie that makes it so efficient. Let's now walk through the logic of the addWord method. We start with the current pointer at the root of our trie. Then we loop through each character in the input word, and for each word we check if a path for it already exists from the current node. And this is where the implementation differs slightly between Java and Python because of our data structure choice. In Java, we are using an array, so we convert the current character into an index from 0 to 25 using the classic trick of subtracting the ASCII value of A from the character itself. and check if the value at that position is null. In Python, it's a bit more straightforward because we are using a dictionary. So we just check if the character is already a key in the children map. So if a path doesn't exist, we create a try node and link it up. And in any case, we advance our current pointer down to that child node. And once the loop finishes, the current pointer is at the node corresponding to the last character of the word, and hence we mark its isEndOfWord flag as true. And now let's see how do we search the words. First, let's search the word pad. Now searching will involve two simple rules. If we see a normal letter, we must follow the specific path in the try. But if we see a dot wildcard, we must explore every child path of the current node. Let's see this with action. And again we start at the root node and we check if root has a child for p, and the answer is no. So our search fails and we return false immediately. This is way better than the naive approach because there we had to search through all the words in the data structure. Now let's search bad into the try. And again we start at the root node and first character we see is B. So we check if the root has a child for B and the answer is yes. So we move to the node B and next character is A and we check if B has a child A and the answer is yes. So we move to it. And finally the last character is D and node A has a child for D. So we move to it. And this was the last character in the search word. So here comes the crucial check, which is the endOfWord flag set on the D node? And the answer is yes. That means we found a complete word in this path. So we must return true. Next comes the interesting case, the search with the wildcard. And again we start at the root node. And the first character we see is dot. And as it is a wildcard, the rule for wildcard is that we must check every child of the current node, in this case root, to see if any of them can complete the match with the rest of the word AD. And this try all paths problem is a perfect scenario for recursion. We can simply ask each child node to solve the exact same problem. Can you find AD starting from yourself? So say we go to the first child, in this case the node B, and we make a recursive call to search for AD starting from here. And the next character we see is A, and we check if B has a child for A and the answer is yes. So we move to node A. And next character we see is D, and we check if A has a child for D and the answer is yes. So we move to it. And since it was the last character in the word, we must also check if isEndOfWord flag set on the node D, and the answer here is yes. So we will return true from this path. So we found one word which matches the pattern .ad, and hence we immediately stop and return true without ever checking the paths starting with D and M. Now let's add the word bug to the try to see the example on the backtracking. And again we start with the root node, and here first character we see is B, and we can see that root has a child for B. So we move to it, and the next character is U, and since the node B doesn't have the child for U, we create it from B and link it. And finally for the last character G in word, we create the child node G and mark its isEndOfWord flag to true. And now let's search for pattern B.G to understand how backtracking will work. And again we start at the root node and first character is B, so we follow the path to the node B, and next character is dot. So this is our decision point. The wildcard rule says that we must match the rest of the word G from every child of the current node B, and B has two children A and U. So let's go to them one by one. Let's say we go to the child A first. So let's make a recursive call to A, and now the next character is G. So we check if A has a child for G and the answer is no. So we return false from this path and backtrack to node B. and make the second decision where we go to the child U and again check if U has a child G, and the answer is yes this time. So we move to it, and now since we have reached the end of the search word and we are at character G, we check if there is a is end of word flag set on the G node, and answer is yes to this as well. So this path is a success and hence we return true. And because the recursive call for the node U path returned true, the original search for b.g succeeds as well, and hence we will return true. Now let's look at the case when the search will fail. For example, we search for string b.s, and here the search is very similar to previous search b.g, just that when we come to node U, we will only find the child G and no S, and hence we will return false. And since neither of the paths from B, that is A and U, have any child for character S, the overall search will return false. Now let's look at the search logic. The main search method is a simple wrapper that kicks off a recursive helper function, search in node, where we pass in the current word with index 0 and the starting node as a root node. This helper function's job is to answer the question, can the rest of the word be found? That is, the word starting from this given index up till the end be found in the trie starting from this given node. And first we have the base case for the recursion. If the current node is null, that means we have reached the end of the current path, but the characters in the word remain. So we couldn't find this word and hence we will return false. And then we have the second base case, which is if we have processed the entire word. In this case, index is equal to word length and we have successfully traversed a path. Now all that matters is whether this path forms a complete word. So we return the nodes is end of word flag. If it is true, then we have found a complete word. Otherwise, we haven't. And now that we have handled the base case, we get the current character from the word at the given index. And first we check if this character is a wildcard dot. If it is, we have to explore all possibilities. So we loop through every child of the current node, and for each child we make a recursive call calling search in node method with the next index and that child node. If any of these recursive calls return true, it means we have found the match down that path, and so we can immediately return true. And if we finish the loop and none of the child resulted in the match, we return false. However, if the character is not a dot, then the path is fixed. So we find the correct child node corresponding to this character, and then we make the recursive call, moving to that child and the next index, and return the result of this call as our answer. Now, the overall time complexity for addWord will be O of L, where L is the length of the word, because for each character we perform one simple operation, either following a pointer or creating a new node and then following a pointer. And the time complexity for the search will be O of L as well, in case of an exact match, as we just traverse down a single path. And for a wildcard search, the time complexity is bounded by the total number of nodes in our trie, resulting in the time complexity of O of n into L, where n is number of words and L is their average length. As in this worst case, we may have to go through all the nodes in the trie, and theoretically, even more worst case can be when this trie is completely full. In this case, the time complexity can be O of 26 to the power of L, and the space complexity will be O of n into L as well. This is in case the words don't share the prefix, but in practice it should be better because the words do share the prefix. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.